So in this video, we're going to talk about how you can determine the principal stresses in 3 dimensions for a given state of stress. So if we have a stress element and we cut the stress element at a certain plane, which would be one of the principal planes, on this plane, the shear stress is going to be equal to 0. So on this element, we still have our components, our normal components of our stresses, sigma y, sigma z, and sigma x, and we still have all of our shear components. We have tau xy, we have tau yz, or tau's, so we have all the various shear components here, um, and we have, so, so if we have all of our shear components and our stress components on this matrix, we know that they have to balance out with the principal stresses in the new orientation. And we know that these are related by our directional cosines x, y, and z. So, um, so we can simplify this equation down and to be a single equation where we have our one matrix, which is equal to our stress matrix minus the principal stress matrix, our principal stress value times I times our eigenvector v, which we'll define using our directional cosines. So we know that the determinant of sigma minus sigma p times I is going to be equal to 0. So we'll use this to find our principal stresses. So um, so we can do um, so if we take that determinant, what we end up getting is we get a from this determinant we get a cubic polynomial. Um, so if we solve our cubic polynomial, what we'll end up getting is we'll get 3 values for sigma p. We'll get sigma p1, sigma p2, and sigma p3. Now, we'll note that these 3 values for our principal stresses, we'll rank them in terms of their absolute magnitude. So sigma p1 is the largest principal stress, and sigma p3 is the smallest principal stress. What I mean smallest, what I really mean is the most negative principal stress. So sigma p3 could be equal to 0, but if sigma p1 and sigma p2 are still greater than 0, then sigma p3 is still our principal stress. All right. So so once you have your 3 principal stresses, you can plug in the values of sigma p here into to determine the directional cosines nx, ny, and nz relative to our original coordinate system. We need to define we need to plug in sigma p 1, or you can plug in sigma p2, or you can plug in sigma p3 into 2 out of the 3 equations listed here, and you have to plug in and the last thing you need to do is you need to use this equation here as well. So you have 3 equations, you have 3 unknowns, and you can solve for nx, ny, and nz to relate the principal stress, to relate the original x, y, z coordinate system to the particular principal stress that you plugged in. Okay? You can also use the vector method to do this, to find the eigenvalue. So you could plug in sigma p into the following equation here to find your nx, ny, and nz values as well. Okay, so whatever method you choose to find the eigenvectors, that's totally fine. And then you can use the same and then you'll have to use this cubic root equation to find sigma p1, sigma p2, and sigma p3.